Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics and math. Today I'm going to be going through some high school level and college level calculus problems. Be sure to check out the links in the description if you're in need of any extra homework help or like some one-on-one tutoring. So let's jump in. So we would like to evaluate the indefinite integral as an infinite series. So to do this, first what we're going to do is find 10x, and then you need to find arctan x squared in terms of an infinite series, and then we integrate that in infinite series. Okay, so we already know that arctan of x is equal to, of course, inverse tangent, and that is equal to the integral of 1 over 1 plus x squared. And now we're going to use our friend here, the fact that 1 over 1 minus x is equal to the infinite series of x to the power of n. So what that means is 1 over 1 minus negative x squared is going to be the infinite series of negative x squared to the power of n, because that is what we're putting in to find the infinite series for inverse tan. That's the first step. We can pull out the negative 1. So negative 1 n x to the power of 2n. And that's going to be what this is equal to. And so next up, we know that arctan of x is equal to the integral of 1 plus x squared, and that's going to be the integral of this summation, since we found that the two are equal. So both of these terms don't have any x reliance, but this one does. And so we're going to remember the exponent rule, which is just the fact that the integral of x to the a dx is equal to 1 over a plus 1, x to the a plus 1. And so in this case, our a is 2n, so a plus 1 is 2n plus 1, x to the power of a plus 1 is x to the power of 2n plus 1. So all of that will mean that arctan of x is going to be equal to this infinite series all over 2n plus 1. Next up, we want to find arctan x squared, as we said here. So we do that by simply substituting x with x squared. So I just multiplied this by 2 to get the new exponent. And then next up, we're going to be integrating this. So the integral of arctan x squared over dx is going to be equal to the integral of this summation. And so we're going to be using this exact same rule, except now our a is 4n plus 2. So a plus 1 is going to be 4n plus 3, which means that this is going to become this infinite series And then we need to remember the fact that the integral is unbounded. So we will have a plus c. We can have the c at the beginning to make it less confusing. So it'd be c plus our infinite series. And that's going to be your final answer. Okay, next up we're going to be using L'Hopital's rule and our function. First we need to understand what L'Hopital's rule is, and that just simply states that if the limit as x approaches a of f of x is equal to 0, or it's equal to positive infinity over negative infinity, or the limit of g of x as x approaches a is equal to 0, or again the same case, positive infinity over negative infinity. What that is going to mean is that the limit as x approaches a of f of x over g of x is going to be equal to the limit as x approaches a of the derivative of the two. And so we're going to use that on the question that we've been given here. And we have, we are looking for the limit as c approaches 0 from the positive end of m g over c into 1 minus e to the power of negative ct over m. And then we're going to rewrite this in a different form so it's easier to put it into this form. C approaches 0 is going to be equal to 1 minus e to the negative ct over m all over c over m g. And then next up we have that this is equal to our f of c and this is equal to our g of c. We're going to take the derivative of both of them so that way we can get the answer to this by having this. And so it will be equal to the limit as c approaches 0 from the positive side. The derivative of this is going to be negative 1 by negative t over m. So that simply will become t over m multiplied by e to the negative ct over m. This can be done by just simply using u is equal to negative ct over m and applying the chain rule to get the derivative. And then the derivative of this is just going to be 1 over mg. Okay, and so let's rewrite this, or we can take the limit first. The limit as this approaches 0 from the negative side will become 1. And so what we'll be left with is t over m over 1 over mg. This is going to be t over m times mg. The two m's will cancel and that will just leave us with t times g. And that's going to be our final answer. Okay, on to our next question. We want to prove the power rule when it comes to derivatives. We can do that in the case that the power is 10, or we can do it generally by setting 10 is equal to a. Let's do what's been asked. So we're going to set the power equal to 10. And so we need to remember the general formula for the derivative. And that would be the limit as h approaches 0 of x plus h. Sorry, f of x plus h minus f of x all over h. And so if we want the derivative of x to the power of 10, we're just going to put x to the power of 10 as our function. And so it would become the limit as h approaches 0 of x plus h to the power of 10 minus x to the power of 10 over h. Now what we're going to do is we're going to use binomial theorem to expand this. It's going to leave us with only one term with a h that can cancel. The rest will have higher order h's that won't cancel. So as h approaches 0, the rest of those terms will cancel and leave us with one thing. And so let's just write down binomial theorem. And that just states that x plus a to the power of n is going to be the summation from k is equal to 0 to n of n choose k multiplied by x to the power of n minus k, a to the power of k. And so that means that x plus h to the power of 10 would be the summation from k is equal to 0 to 10 of 10 choose k, x to the power of 10 minus k, h to the power of k. Let's write what that is going to be. So start with 0, 10 choose 0, x to the power of 10, h to the power of 0, plus 10 choose 1, x9, h1, 10 choose 2, x8, h2, 10 choose 3, x to the power of 7, h cubed, 10 choose 4, x to the power of 6, h to the power of 4, and just continue like that. Okay, and then if we just remember the fact that n choose k is going to be equal to, the formula for it should be, n choose k is going to give us, sorry, I forgot the formula, but it's quite common. Yeah, it's going to be n factorial over k factorial into n minus k factorial. And so you can go about calculating these by hand, the individual 10 choose 0, 10 choose 1, etc. You can also do it with your calculator, which is how most would, because typically during an exam you need to work fast. So it is going to become x to the power of 10 plus 10x to the power of 9 by h plus 45 plus 120 plus 210 plus 252. And then it starts to form a sort of mirror effect. And so you'll have 252, 210, 120, 45, 10, and lastly h to the power of 10. And so now we have that all of this is equal to x plus h to the power of 10, which means that x plus h to the power of 10 minus x to the power of 10 we'll cancel out this first term because you technically had an x to the minus 10. So these two cancel and it will leave the rest. And so that's going to be the first part of what we're doing. But we notice here that we're going to divide out h and then take the limit of whatever is left as h approaches 0. So let's divide out h, different color. So this h will cancel, this h will drop, 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 drop. And so what that will leave us with is 10 by x to the power of 9 plus a bunch of terms with h's, which means that when we take the limit as h approaches 0 of what we have left up here, all of these other terms that still have h's are going to become 0 as h becomes 0. And it'll only leave us with 10 by x to the power of 9, which is exactly what we expected. And so this would be equal to the derivative of x to the power of 10. Okay, next up we would like to find the integral of e to the power of x squared dx. How we are going to do that is we are going to apply linearity in order to convert it to a form that has an identity integral, and then we're just going to give the answer in the format of the identity integral. And so we're going to set 1 is equal to 2 over root pi by root pi over 2. And so we're going to multiply this by 1. So it can become the integral of 2 over root pi by root pi over 2 by e to the power of x squared dx. And then what we're going to do is we're going to move this out of our bounds. We can technically move both, but we don't want to do that right now because we're trying to get it into a specific form. So it'll become root pi over 2 into the integral of 2 over root pi e to the x squared dx. And this is the special identity integral that we're looking for. And it is the imaginary error function. And so that means that the integral of e to the x squared dx is going to be root pi over 2 multiplied by the imaginary error function. And then it's unbounded, so don't forget about the plus c. And that's going to be your final answer. Okay, so suppose f is the differentiable function of x and y, and a function g of u and v is equal to the function f of u and v. And so given the table of values, you want to find the derivative of g with respect to u at the point 0, 0, and find the derivative of g with respect to v at the point 0, 0. And so we're going to be making use of the chain rule. And how we're going to do that is we're going to note the fact that the derivative of g, these are partial derivatives, the derivative of g with respect to u is going to be the derivative of g with respect to x multiplied by dx over du. Okay, and so what we're going to do is we are going to set g u v is equal to a function of x and y. We're going to set x is equal to e to the u plus sine v, y is equal to e to the u plus cos v. And so when I say that I want g of x, this derivative, since g is in terms of u and v, this technically doesn't make sense. So what instead I'm going to write is f of x with respect to x and y. So they're the same function. Instead though, here I have terms in terms of u and v. Here I'll have terms in the sense of x and y, but that x and y themselves will have terms in terms of u and v. And so now what is going to happen is you'll have dg over du is equal to, instead of the derivative with respect to x, we'll write it in this form. So fx at x, y multiplied by dx over du plus fy at x, y multiplied by dy over du. And now, additionally, we want this evaluated at 0, 0. Which means we will evaluate the partial derivatives at 0, 0, multiplied by dx over du at 0, 0. Dx over du will become eu plus cos v, and at 0, 0 that will become 1 plus 1. Alright, just one moment. So 2. Additionally, this one will become eu minus sine v, and that will just become 1 minus 0, so 1. So dx over du evaluated at 0 is going to be 2, plus the derivative with respect to y at 0, 0, multiplied by dy over du at that point, so by 1. And then luckily we have been given fx and fy at these various points. So fx at 0, 0 is going to be 4, and fy at 0, 0 is going to be 8. Oh, but please note, I've made a mistake here that people are prone to making, and that is the fact that we want gu 0, 0. And gu is in terms of u and v, which means we're setting u and v equal to 0, not x and y. That's where the mistake has occurred. And so what that means is if u and v are equal to 0, x is 2 and y is 1. And so instead of fx 0, 0, we'll have fx 2, 1 here. And similarly here, again, we'll have fx 2, 1, because you have the x values in here, not the u values. And so now when you come and look at the table again, fx at 1, 2 is 2. So it becomes 2 by 2, plus fy at 2, 1 is 5. So 5 by 1, and that will become 4 plus 5, which is 9. Sorry, I'm just ensuring everything makes sense here. E0. And that's going to be your final answer. Next up, we're going to do the same thing, but with respect to v. And so just remember, and so we know that this is fx, and we're going to be evaluating it at u is equal to 0 and v is equal to 0. And this one is going to be fy evaluated at those same points. And so we have stated that x is equal to e to the u plus sine v. So x at that point, at the point 0, 0, is going to be equal to 1 plus 0, so 1. Y is going to be equal to and I think the same mistake occurred above. Sorry, so this should be f1, 2 and 1, 2 because I'm not putting in the derivative of x at 0, 0. I'm putting in x at 0, 0. And so this should also be f of 1, 2, f of 1, 2, and this should give you fx at 1, 2 is 2 by 2 plus fy at 1, 2, which is 8 by 1. 5 by 1, my apologies. Let me just ensure everything else is okay. This evaluated at 0, 0 is going to give us 2, and it's going to give us 1. And so this should give us a final answer of 9. It gets a little tricky because of how many different functions you're using, and you can slip up with the terms as I did before. It just matters that you go through things and catch those mistakes before you submit your work. And so lastly, we have dx over dv is going to be equal to, see, similar here, we have the same mistake that I made. The derivative with respect to u is just going to be e to the u for both of them. And so this is going to be equal to 1, this is going to be equal to 1. So we are going to be multiplying both of these by 1, and instead it should give the answer 2 by 1 plus 5 by 1, which is 7. And that's the correct final answer. So dx over du evaluated at 0, 0 is, over dv is going to be equal to cos v, and evaluated at 0, 0, that's going to be 1. dy over du evaluated at 0, 0 is going to be negative sine v. This is v. And that's going to be negative 0. And so now when we put that all together in this formula, we will have dg over dv evaluated at 0, 0 is going to be equal to f of x evaluated at 1, 2 multiplied by dx over dv at that point, you know that that's 1, plus the derivative with respect to y evaluated at 1, 2 multiplied by 0. And that is going to give us 2 by 1 plus 5 by 0, just leaving us with 2. And that's going to be your final answer for this one. Next up, we would like to prove the identity that e to the negative ix is equal to cos of x minus I sine of x. We're going to do this using Maclaurin series. And so first we just state all of them. So e to the x, the Maclaurin series is the summation from n is equal to 0 to infinity of x to the power of n over n factorial. And that would be starting with 0, and this would become 1 plus x squared over 2 plus x cubed over 3 factorial, and you just keep going like that. Next up, we'd like to state what cos of x the Maclaurin series is going to be, and it is going to be the summation from n is equal to 0 to infinity of -1 to the power of n, x to the power of 2n over 2n factorial. These can all be found just using the formula evaluated at 0. So that would be -1, 0, x, 0, and just keep going. And so this would become everything to the power of 0 is 1. Minus x plus x squared over 2 factorial. Wait, just one moment. The summation is going to actually work out to look like 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial plus, and it goes on like that. And that's because of the fact that any odd number derivatives, of course, are signed and evaluated at 0. That would cancel out the coefficient with a 0. That's why you have x squared, x to the power of 4, so on and so forth. Sine x, let's just finish this up, would be -1 n x to the power of 2n plus 1 over 2n plus 1 factorial. And so that would be the missing terms here, and be x minus x cubed over 3 factorial plus x5 over 5 factorial plus continue. And so now we are going to put in e to the negative ix, and the summation should become 1 it should become 1 minus ix so 1 minus ix in brackets plus ix squared over 2 factorial plus ix cubed over 3 factorial and you continue that way. And then now we just need to use the properties of I. We know that I squared is equal to, I to the power of 2n is going to give us -1. I to the power of n is going to give us, 2n plus 1 is going to give us -I. Because it would take out all of the 2n and leave you with the -1 times I. And so what that means is all of the odd numbered powers here are going to become -1 in front of I, and all of the even numbered powers here are just going to become -1. And so when we write that out, that will become 1 minus ix minus x squared over 2 factorial plus ix cubed, is supposed to be plus ix cubed over 3 factorial plus x to the power of 4 over 4 factorial minus ix to the power of 5 over 5 factorial, and you go on like that. And now we are actually going to separate this into 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial plus, so it's all of these even numbered terms that don't include an I. And I'm going to subtract off I, So the negative I that are in front of the other odd numbered terms, leaving x minus x to the power of 3 over 3 factorial plus x to the power of 5 over 5 factorial, and you go on like that. And we notice that these are actually summations that we know, namely the one that we wrote down for cos. And the one that we wrote down for sine. Except now, yeah, all over 2n plus 1. And so what that means is it will become cos x minus I sine x is equal to e to the negative ix. And that is what we're looking for initially, so it's been proved. Next up, we want the derivative of the inverse secant of x cubed. And so how we're going to do this is we're going to rewrite arc secant of x cubed is equal to y as the secant of y is equal to x cubed. And then we take the derivative of both sides. And then we need to note that this will simply be equal to secant y. Secant y by tan y, all multiplied by the derivative of y itself. So the derivative of secant of something, which is secant y by tan y, multiplied by the derivative of that something. So y is equal to d over dx of x cubed. So secant of arc secant x cubed multiplied by tan of arc secant x cubed into d over dx arc secant x cubed is going to be equal to, we know that this derivative is 3x squared. So it's going to be equal to 3x squared. And then we're just going to isolate this. And we can rewrite this as simply x cubed. So it's going to become that the derivative of arc secant of x cubed is equal to 3x squared over x cubed into tan of the arc secant of x cubed. Let's cancel out these x's. And this will leave us with our final answer that the derivative of what we're looking for is equal to 3 over x into the tan of arc secant x cubed. And that's going to be your final answer. Okay, next up we want to find the antiderivative that satisfies the initial conditions. And so we have, if we write it in the vector form, and so in order to find RT, what we're going to do is we're going to integrate all of them. Okay, and then next up we identify the answer for all of these integrals. So the integral of 1 plus t squared dt is a known integral for arctan t. The integral of t to the negative 2 dt will give us negative 1 over t. Lastly, the integral of 1 over t dt will give us ln of the magnitude of t. Okay, and then let's not forget that the integrals are all unbounded, and so there should be a plus c. And so if you rewrite it in its initial form, we will get that RT is equal to arctan t by I plus negative 1 over t by j plus ln t by k, all plus c. And lastly, we have that the initial value problem R1 which should be equal to arctan 1 by I plus negative 1 over t, so negative 1 over 1, which will just be negative j. So negative j plus the ln of 1 is 0, so 0k plus c should all be equal to 2i. Next up, we're just going to isolate for c. So we get c is equal to 2 minus the arctan of 1, which is going to be pi over 4. So let's just write that down for ourselves. The k is 0, so it cancels. And then isolate for c, so it becomes 2i minus pi over 4i plus j. So that will become 2 minus pi over 4i plus j. And then now we are just going to move all of this back into our initial one, because it's just a constant. So we get that RT should be equal to the arctan of t by I plus negative 1 over t by j plus ln the magnitude of t in the k spot plus the c that we just found plus j. And then we're just going to collect like terms so that it can become arctan t plus 2 minus pi over 4i plus 1 minus 1 over t j plus ln t of k is equal to our RT. And that's going to be our final answer. Next up, we would like to integrate secant cubed. And we are going to be using integration by parts. And so if we use the acronym of inverse, trig, logarithmic, algebraic, trig, exponential, we bump into inverse trig first. And so we'd set u as equal to secant of x, which means dv is going to be equal to secant squared of x dx. Now what this means is that if we use the formula that the integral of u dv is equal to uv minus the integral of v du, and we find the numbers that we need to find, so du is going to give us secant x tan x dx, and v is going to give us tan of x. And so we're going to plug in all of this into here, and we get secant x tan x minus the integral of tan x into this, and that would be secant x into tan x minus the integral of tan squared x secant x dx. And so next up, we're going to want to evaluate this integral so that we can find the answer here. So for this one, we're going to use the fact that the integral, first off, the identity that tan squared x is equal to secant squared x minus 1. You're going to plug that in here, and it becomes the integral of secant squared x minus 1 into secant x dx, and that is just the integral of secant cubed x minus secant x dx. And so now we're going to plug that right back in here. So it becomes the integral of secant cubed x dx is equal to secant x tan x minus the integral of secant cubed x plus, since we're going to separate this out, so plus the integral of secant x dx. The reason why we split it up is so that we can bring this to the other side since the two are identical. Then it becomes 2 multiplied by the integral of secant cubed x over dx is going to be equal to secant x tan x plus the integral of secant x dx. And so we see there's another integral that we're going to need to figure out again. So let's go about doing that. The integral of secant x can be found if we set 1 as equal to tan x plus secant x over tan x plus secant x. So we're multiplying it by 1 over dx. This becomes the integral of secant x tan x plus secant squared x over tan x plus secant x dx. And the reason we did all of this is because if we set u as equal to tan x plus secant x, then du over dx will give us our numerator here. So secant x tan x plus secant squared x. So dx is going to be du over this, which means that when you put it all together, we get 1 over u du, because these two will cancel. And so we know that the answer here would be ln the magnitude of u, and simply put back in the u in terms of x. And now we're just going to put this all right back in here. So it becomes 2 times the integral of secant x dx, which is what we're looking for, is equal to secant x multiplied by tan x plus the ln of the magnitude of tan x plus secant x. And since we have what we're looking for and there's no other integration signs here, we can now isolate it. So it becomes the integral of secant cubed x over dx is equal to 1 over 2 into everything that we have here. And then don't forget about the plus c because we have boundless integration. And that's going to be our final answer. Next up, we want to find the area between two curves. We're going to use the calculus 3 equation. And so we are going to set D as the region in xy coordinates as x goes from -2 to 4, And additionally, as y goes to, so we need to figure out which one is the lower valued one. And so let's just pull up Desmos. And so we have x cubed minus 1. And we have x squared plus 3. Additionally, you could find this out without Desmos by mentally plotting it in your head. So you find the point where the two intersect. We see that it is at the point x is equal to 2 and y is equal, to 7. And that's clearly in the middle of this. And so for half of the function, we have, not half, for half of the question and the integration from -2 to 2, we have that x squared plus 3 is higher than x cubed minus 1. And then beyond that point, from 2 to 4, we will have x cubed minus 1 is greater than x squared plus 3. And so what that means is that we'll instead have two regions. So from x is equal to -2 to 2, we will be integrating from the lower bound is going to be x cubed minus 1. And then we'll have another region. That would be over xy2, but now it will be from 2 to 4. And instead, x squared plus 3 will be the lower bound. And so clearly, since we want the area of these two regions, we can just add them up when we do the integrals. So it would be from -2 to 2, and from x cubed minus 1 to x squared plus 3. And then we're just integrating dx dy plus the integral from 2 to 4. And now we have the lower bound of x squared plus 3 to x cubed minus 1. Again, dx dy, dy dx, because we're looking for the area. So this is d1, and this is d2. And so let's go about doing that. It would be -2 to 2. dy is just going to give us y, so it would become x squared plus 3 minus x cubed minus 1 all over dx, plus from 2 to 4 of x cubed minus 1 minus x squared minus 3 dx. Let's simplify these a little bit to become -2 to 2 of x squared minus x cubed plus 2 over dx, plus the integral from 2 to 4 of x cubed minus x squared minus 4. And this is all over dx. And we know how to find these integrals. This will become x cubed over 3 minus x to the power of 4 over 4 plus 2x. And this is from -2 to 2, plus, find the integral here, minus x cubed over 3 minus 4x from 2 to 4. Next up, let's go ahead and find these values. So 2 cubed will become 8 over 3 minus 2 to the power of 4. So 16 over 4 plus 2 by 2, 4, minus -2 to the power of 3 over 3. -2 cubed is going to give us -8. So minus will become positive. -2 to the power of 4 is going to give us a positive. And remember, we are doing the negative here. Additionally, we could just write them out. So this will become -8 over 3 minus 16 over 4 minus 4. And then we write out this one to become 256 over 4 minus 64 over 3 minus 16. This is all minus 2 to the power 4, so 16 over 4 minus 8 over 3 minus 8. Let's write that all out. 8 over 3 minus 16 over 4 plus 4 plus 8 over 3 plus 16 over 4 plus 4 plus 256 over 4 minus 64 over 3 minus 16 minus 16 over 4 plus 8 over 3 plus 8. And all of this will give us a final answer of 164 over 3 when you add up all of those fractions, and that's going to be your final answer. Next up, we want the integral of sine 2x dx. We will set u equal to 2x. Du over dx will be equal to 2, which means dx will be equal to du over 2. Put that all in, and we'll get the integral of sine u du over 2. Pull out the 1 over 2, so there can become the integral of sine u du. And this we know to be 1 over 2 into negative cos u. And then you put in, we know u is 2x, just put it back in. And it becomes negative cos 2x over 2. And then don't forget that it is without bounds, so don't forget about the plus c. And that's going to be your final answer. On to the last question. We would like the derivative of ln of e to the x. There are two ways to do this. Let's start with the more thorough one. And so what you do is set u is equal to e to the x. And we know that d over dx of ln u is going to be equal to, using the chain rule, let's just write that out, dy over dx is equal to dy over du multiplied by du over dx. And so just going to apply that here so that we can get the derivative with respect to x of ln u is equal to 1 over u multiplied by e to the x. So it can become 1 over e to the x multiplied by e to the x. These two cancel, leaving you with 1. There's another way to do this, which is if you use the exponent rule and the base rule for logarithms. So if we have log a is equal to 1, and additionally log base a of some other number to the power of x is equal to x log base a b. And so now in our question we have log to the base of e to the x. So let's first use this rule. So that it can become x by log to the base of e, and we know that this is going to be equal to 1. So really, we have y is equal to x is the question, and we'd like to take the derivative of both sides. And you know that the derivative of x with respect to x is simply 1, just like we found using the other method. And that is going to be your final answer. And those are all the questions I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified of when we do post online, be sure to hit the subscribe button and the bell right next to it. If you'd like to be able to post questions on your own on the OneClass page, be sure to check out the links in the description. This has been Marlyn from OneClass, and I hope to see you next time.